Good afternoon, sir. The topic I chose to explain is binary codes, error detection and error correction. First of all, we need to know about the computer language. The language of the computer is binary language, which means two numbers, only 0 and 1 are used to represent any kind of decimal numbers, hexadecimal numbers, octal numbers, or words, alphabets, symbols, etc. so that the computer can easily understand and give the output which is required for us. Now first of all, we should know about the coding or encoding. Coding is a process of assigning a group of binary digits or bits to relate some piece of information. Generally, coding is a symbolic representation of info. Binary codes, every decimal numbers, hexadecimal numbers, octal numbers, alphabets, everything are represented in 0 and 1. Bit, these 0 and 1 are also called bit. One byte equals to 8 bits. Normally, nowadays, each decimal number or a word or a letter is being represented in 8 bits or 4 bits. We can also write nibble. Nibble is also equals to group of 4 bits. We mostly use nibble to represent any number. Next, binary codes. Binary codes is nothing but the process of using 0 and 1 to represent numbers, letters, symbols, words, etc. Next, binary codes are divided into 6 types. First one, weighted codes, weighted binary codes. Second one, non-weighted binary codes. Third one, sequential codes. Fourth one, reflected codes. Fifth one, alphanumeric codes. Sixth one, error detecting and error correcting codes. First of all, we will learn about weighted binary codes, which means each and every digit holds some particular weight. Each position has some particular weight. In these weighted binary codes, examples are 8421 codes, BCD codes. BCD codes means binary coded decimal codes. BCD. 8421 codes, 2421 codes, 74 2-bar, 1-bar codes, 5211 codes, etc. are used in weighted binary codes. Each and every position holds some weight. Examples to weighted binary codes are BCD codes. BCD, binary coded decimal codes. 8421 codes, 2421 codes, 5211 codes, 74 2-bar, 1-bar codes, etc. Next, we will learn about non-weighted binary codes. non-weighted binary codes are nothing but they are strictly opposite to the weighted binary codes. Nothing but in weighted codes each position holds some weight. In non-weighted binary codes does not hold any weight. Examples are access3, not accessed, not assigned any weight. To each position. Examples to non-weighted binary codes are access3 codes. Access3 codes can also be written as access3, and gray codes are the example for non-weighted binary codes. Next, we learn about sequential codes. Sequential codes are nothing but each preceding code is one bit greater than its succeeding code. Examples: each preceding code is one bit greater than its succeeding code. Examples for sequential codes are serial codes, binary codes, BCD codes, access3 codes. Next we will discuss about reflected codes. Reflected codes are nothing but it is like a mirror image. For example, the decimal numbers from 0 to 9, the 10 numbers 0 to 9 are written in binary form. If we look at those numbers, we will get a mirror image. They are reflected to any one of the number from 0 to 9. Examples for, we can represent it as 0. 0 reflects 9. 0 is mirror image to 9. 1 is mirror image to 8. 2 is mirror image to 7. 3 is mirror image to 6. 4 is mirror image to 5. Examples for reflected codes are access3 codes, 2421 codes, etc. Now we will learn about representing decimal numbers in binary, in terms of binary code. We will represent 0 to 15 binary code. Now 0 can be represented in binary code as 0 0 0 0. This is 8421 code. This is 8421 code. 0 is not present in 8421, so all are zeros. 1, next 1. Decimal number 1 can be represented in binary code by 8. 8 is not 1. No, 8 is not equals to 1, so 0. 4 is not equals to 1, so 0. 2 is not equals to 1, so 0. 1 is equals to 1, so 1. Next 2. Similarly, 2 can be represented as 0 0 1 0 3. Now 3 can be represented as 2 plus 1 equals to 3. So 1 and 1. 4. Similarly 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. These are the decimal numbers represented in binary codes. Now we will learn to represent gray code. Gray code. Now we will learn how to convert binary code to decimal code. Binary code to gray code. Binary code to gray code. Binary code is converted, for example, we will take a binary code, for example 1011 base 2. This should be converted into gray code. It is like this. XOR operation is used in this. 0 XOR 1 XOR 1. First digit. First binary code to gray code conversion. We consider this example by using XOR operation between these 4 binary digits, binary bits. First digit is represented as it is, and applying XOR operation between 1 and 0. 1 XOR 0 gives 1. 0 XOR 1 gives 1. 1 XOR 1 gives 0. So 1011 base 2 in binary is represented in gray code as it is equals to 1110. We will take another example. For example 1101 base 2. Similarly, by using XOR operation between these 4 bits, first digit is represented as it is. 1 XOR 1 gives 0, 1 XOR 0 gives 1, 0 XOR 1 gives 1. So 1101 in binary is represented as 1011 in gray code. Next, we will learn how to convert gray code to binary code. Now let's take an example. 1011 gray. This is also by using XOR operation. First these bits are written like this. In every conversion, this first digit is represented as it is, but in binary code to gray code conversion we use XOR operation in between the bits, but here we use XOR operation in between the result and the bit, the given bit, next bit, like this. So here we get 1 XOR 0. Next 1 XOR 1 0. Next 0 XOR 1 1. So 1011 in gray code is represented in as 1101 in binary. Next, we'll learn how to get access3 codes. We can easily learn access3 codes from binary BCD codes, binary coded decimals. Binary coded decimals are represented from 0 to 9 using 28421. Similarly, now 0. Similarly, we will represent 0 to 9 decimal numbers as binary codes, similarly as we done before. Now we got 0 to 9 BCD codes to binary codes, decimal codes to binary codes. By using these BCD codes, we can get XS3 codes. XS3 codes means the name itself defines the XS3 codes by adding 3 plus 3 to the binary. Plus 3 in the binary means 0, 0, 1, 1 to each binary, plus 0, 0, 1, 1 plus 0, 0, 1, 1 plus 0, 0, 1, 1 plus 0, 0, 1, 1, like this. We should add this BCD codes and this plus 3 in binary. It gives XS3 codes. By natural adding, it is normal addition. 0, 0, 0 plus 0, 0, 1, 1 gives 0 plus 1, 1, 0 plus 1, 1, 0 plus 0, 0 plus 0 gives 0, 0, 1, 1. This is 0, decimal number 0 in XS3 code. This is decimal number 0 in XS3 code. Next is 0, 0, 0, 1 plus 0, 0, 1, 1. 1 plus 1 is 0. Carry 1. 1 plus 1 is 0. Carry 1. 1, 0. This gives 1, 0, 0, 0. This represents 1, decimal number 1 in XS3 code. Similarly, all this by natural addition we can write. Next decimal number 2 represents 0, 1, 0, 1, 3, 0, 1, 1, 0, 4, 0, 1, 1, 1, 0, 0, 0, 5, 1, 0, 0, 1, 6, 1, 0, 1, 0, 7, 1, 0, 1, 1, 8, 1, 1, 0, 0, 9. These all are XS3 codes. These all are XS3 codes. These are decimal numbers represented in XS3 codes. Next, now we will learn about 2421 codes. 2 plus 4 plus 2 plus 1 gives 9. That means 0 to 9 decimal numbers can be represented by using 2421 codes. 0, 0, 0, 0, 1, 1, 0, 0, 0, 1, 2, 0, 0, 1, 0, 3, 0, 0, 1, 1, 4, 0, 1, 0, 0, 5, 0, 1, 0, 1, 6, 0, 1, 1, 0, 7, 1, 1, 1, 8, 1, 0, 0, 9, 1, 1, 1, 1. Now 2421 codes, these are 0 to 9 decimal numbers represented in binary 2421 codes. Now here there are two two 2's present in 2421 codes, we can get a doubt that how can we represent 2. Because two 2's are there, we can write here one or here one, that is our wish. You can write in any way, it does not go wrong. Next we will learn about 7/4 2 bar 1 bar codes. 7 plus 4 minus 2 minus 1, that gives 11. That means we can represent 11 decimal numbers in the form of 7/4 2 bar 1 bar codes. Let's see. This representation is totally similar to representing decimal numbers in the form of binary numbers. There is no such complexity in this. The way you represent decimal numbers into binary numbers is the same way you represent these 2421 codes or 7/4 2 bar 1 bar codes. Next, alphanumeric codes. Alphanumeric codes are many types. Mostly three types of codes are used. They are ASCII codes. Next, ABCDIC codes. Next, Hollerith codes. ASCII codes are represented in 7 bits. That means 0 and 1s are repeated 7 times, or like 0 1 1 0 1 0 1. These are 7 bits. These ABCDIC are represented in 8 bits. Hollerith codes are represented in 11 bits. ASCII stands for American Standard Code for Information Interchange. Next, this is ASCII code. By using ASCII code, we can represent any kind of numbers, decimal numbers, symbols like punctuation marks, full stops, commas, brackets, and alphabets too. We can represent everything by using ASCII codes. The chart is also provided. Here is the chart. When we see the chart, here we can see exclamation mark, inverted commas, hashtags. These all are the symbols, and 1 2 3 4 numbers are also represented, symbols, and the alphabets. In this ASCII chart, alphabet starts from 65, number 65, decimal number 65, and this decimal number 65 can be represented in binary form, in form of zeros and ones. That means computer can easily understand from it. Here it is alphabets totally. This chart is ASCII chart. Now ASCII code is a 7-bit. It is ASCII code. Everything. For example, any decimal number, it is everything. Any alphabet, it is represented in 7 bits. For example, let me take 30. 30 can be represented in 30 decimal number. We can do like this: 2, 1, 5, 0, 2, 7, 1, 2, 3, 1, 2, 2, 2, 1, 1. We should write in this form, in this way: 1, 1, 1, 1, 0. We got this, but it should be represented in 7 bits. Now we add zeros to the preceding binary. That is equals to 0, 0, 1, 1, 1, 1, 0. 1, 2, 3, 4, 1, 2, 3, 7 bits. This is binary of representation of 30. Similarly, 31, 41, etc. everything can be represented by using ASCII code. Next, error detecting or error correcting codes. Error detecting or error correcting codes are divided into 2 types. They are parity codes, second Hamming codes. Again, parity codes are divided into 2 types: even parity or parity. Even parity. For example, if we take a binary code 0, 0, 1, these total parity codes depends upon number of ones present in the binary codes. Here the number of ones are equals to 1, that means odd. Now the even parity bit comes 1 and odd parity comes 0. That means opposite. If the number of ones are odd, even parity equals to 1. The number of ones are even, odd parity equals to 1. Similarly, we can write 0, 1, 0. Say 0, 1, 1. Here the number of ones are 2. That means even. Even number of ones means odd parity equals to 1, even parity equals to 0. Next, 1, 0, 0. Next, 1, 0, 1, 0, 1. 1, 1, 0, 0, 1, triple 1. Number of ones are 3, so even parity bit equals to 1, odd parity bit equals to 0. Next, even parity bit is nothing but adding one extra bit to the MSB or LSB to get the required output. It's known as parity codes. For example, 35. 35, we can write 35 in binary as 2, 1, 7, 1, 2, 8, 2 4s, 2 2s, 2 1s in this form. Now 1 0 0 0 1 1. base 2. The number of ones are 3. So even parity equals to 1. So this one is added to the MSB bit. 1 1 0 0 0 1 1. This is the MSB bit. This is the LSB bit. This is total binary representation of 35. Similarly, we can represent any kind of decimal numbers, etc. Next, we learn about Hamming codes. Hamming codes, it's nothing but number of parity bits in between the given data. The general structure of representing Hamming code. There is a format to represent Hamming codes. The format is P16, X15, X14, X13, X12, X11, X10, X9, P8, X7, X6, X5, P4, X3, P2, P1. This is the general format of representing Hamming codes. We'll take an example. X given x is equals to 1011. This is the given original data. We should find Hamming code to this given original data. Find with even parity. Now this can be written as this. This here P represents parity, X represents original data. Now we can write this given original data as X7, X6, X5, P4, X3, P2, P1. Here X7, X6, X5, X3. These are, we should find these parity bits. Now we'll make a table P4, P2, P1. That is 2 power 0 means 1. 2 power 1, 2. 2 power 2, 4. 4, 2, 1. Similarly, we write 0 to 7. Zero, 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 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Now let's check out this row P1 column is P1 totally. Let's check this. To find out this parity bit P1, we're gonna do is first of all let me check where are the ones present in this P1 to find out. 1 is present in 1, in 3, in 5, in 7. 1, 3, 5, 7. 1, 1, 1. The number of ones are odd, so even parity becomes 1. So P1 equals to 1. Next we should find P2 by considering these P2 column. Now also we will check the number, where are the ones present. 1 is present at 2, 3 and 6, 7. We get here number of ones are 2, so even parity is equals to 0. P2 equals to 0. Similarly, P4. Number of ones are present at 4, 5, 6, 7. 1, 0, 1, 1. P4. See, here also the number of ones are 2, therefore even parity is equals to 1. Sorry, even parity is equals to 0. P4 equals to 0. Therefore, here we write P4 equals to 0, P2 equals to 0, P1 equals to 1. Therefore, for the given original data, the Hamming code is 1 0 1 0 1 0 1. This is the Hamming code for the given original data. Similarly, we can convert Hamming code into the original data. For example, the given Hamming code, let us consider. One zero one one zero triple 101. Hamming code is this, so we can write it as 1 0 1 1 0 1 1 1 0 1. Okay, x10, x9, p8, x7, x6, x5, p4, x3, p2, p1. If the given data is a Hamming code, we should remove the parity bits. We should remove the parity bits and write the remaining code. Therefore, original data. By removing parity bits, we get 1 0 1 0 1 1. Therefore, the original data is this. Thank you, sir.